Hello, good morning to everyone. Welcome to the CoUDlabs webinar. I can see that the attendees are coming in. But maybe without further ado, we will start, and then we will give a little bit of time in this introduction for people to go join in. Well, today, 15th of March, we have another webinar of CoUDlabs, the collaborative urban drainage laboratories Horizon 2020 project funded by the European Union. And we are here today to talk a bit about optical observations in urban water systems and rivers. And there is a very nice group of presenters today. If I can go on. We will have a series of small presentations of about 10 minutes from different concepts of optical observations. It's a very, very nice layout of speakers. We will have in the first part of the morning, we will have several presentations, especially regarding velocimetry, discharge measurements, and in general, the observation of flows. And those will be applied to both rivers and urban drainage systems. And therefore, we'll have a small coffee break around 10:30. And later, we will come back with another 4 presentations regarding different applications of monitoring processes, often using deep learning applications for different dynamics related to flooding, to water quality processes, or other asset monitoring in pipe systems. So without further ado, we are going to start to follow with the program, and we are going to have a first presentation provided by Dr. Juan Naves. Juan is a postdoctoral researcher at the University of Coruña, and he has an extensive experience with providing different kind of applications of PIV, especially in large scale, to monitor velocimetries around large scale urban structures. So maybe if Juan, you can start sharing your screen and becoming a presenter, it will be very nice to have you in.
I think that. Hello, Antonio. Good morning, all. I think that everything is fine now with the screen. And just to not waste more time, thank you for the introduction, Antonio. And I want to start today, or my plan for today, now is working, is to present you very briefly 3 cases where we are using these imaging techniques to urban drainage system. The 2 first cases is on a large-scale urban water facility that we have here in the laboratory in the University of Da Coruña. The first one is how we are measuring to the runoff velocity maps in an urban catchment surface using the large-scale PIV with low-cost equipment. The second case is how we are trying to measure or to take something from some sediment wash-off experiment that we carry out in the same facility. And then very briefly, a third case about how we are trying to start transferring all of this knowledge and all of this experience to field work in a sediment retention tank. This is our large-scale facility. It consists of a rainfall simulator of 100 square meters, and it is a cross of streets, as you can see here. And we have a roadway, the pathway, and also 4 blocks that now are with conventional roofs. All the water or the runoff produced by the rainfall simulator is drained to a pipe system through these 4 gallipots, and everything is conveyed to a common outlet. We are interested in using these imaging techniques to get data, for example, mainly surface velocities, to understand better process related with rainfall runoff transformation and this sediment transport in urban catchments, and also use this data in the final objective to validate or calibrate or develop a high resolution to the models of urban drainage models. For this purpose, I start with the first case. We have installed 4 measuring points along the facility, as you see here, and each of these points has 2 cameras based on Raspberry Pi and 2 types of lamps. The first two, or the first type of lamp, is the conventional LED lamp that is turned on here in the above image, and these lamps are used to highlight tracers. That in this case we are using some bubbles that appear naturally with the impact of the raindrops on the runoff. We have also other 2 lamps that are ultraviolet light, and that is for highlighting fluorescent particles that we also use as tracer in another experiments. And for this, we have to use a more conventional camera, let's say expensive one. These Raspberry Pi based cameras are 2 combination. The first one is a Raspberry Pi 4 with a high quality camera, and it costs around 200 euros approximately. And we are covering with this area of around 1 meter of the surface. And you can see here how we record, or we use that bubbles as tracer. Measuring PIV in streets or in urban environment has some challenge, like the presence of rain always that can interfere with the images, but also with the movement of the tracers. If one drop impact just very close to the trace, it can move suddenly and produce some chaotic movement there. The other combination is a Pi camera and a Raspberry Pi 0W that it costs less than 50 euros, and this is used just to see a wide area of around 6 square meters, more or less, and has a less processing capacity. Just a very quick description of the procedure. We have the two consecutive frames. We rectificate, we filter it, and then we process it with the open PIV software with the code. And after a filter of the velocity results and then an average, we can get some nice results like this of the velocities of these tracers on the surface. If we do this with all the points that we are measuring, or we are framing with the lens, we can have some velocity distribution along the facility for variable range, synthetic rain. These experiments, we use these experiments also to compare one system with the other and try to kind of validation of the technique. For that, we compare the results that I showed you with the results that take it from the other system based on Raspberry Pi, and we take the one common point, 30 centimeters by 30 centimeters, and we do an average, and we represent with the time, and we can compare with both systems. And also, the cheapest one has some problem at the beginning because the low resolution and the wider area that we are covering in the first moments of the the test, there are less bubbles in the surface, so it has some difficulties, and also we have a little less resolution in the measurement, but both results are fitting quite well. Changing to the second case on the wash-off experiments, we have used the same facility, and we focus now in this area where we have distributed different loads and different types of sediments in the curve, and then we make rain and we analyze how these sediments are washed by the rain, and we can take samples here and also detailed hydraulic characterization. Inside of this hydraulic characterization, we have performed a LSPIV technique with fluorescent particles. This looks like this. And we use these fluorescent particles because the bubble has problem with complex flows. For example, in the cross of two perpendicular flows, these bubbles stay in the barrier from one to the other, and we wanted to have like all the area measured. This can be seen in the results of velocities, and we realized that we have some preferential channel here due to the different elevations or some small variability in the elevation of the surface. It looks smooth, but it's not completely flat. And as you see here, you can see what the deposition area are. Are this area that it has not velocities, and this area where the two flows interact. So this technique is helping us to understand the processes. In this experiment, we have also recorded the washing of the sediment itself, and we are trying or starting to estimating first the amount of sediment that still remain on the surface during the experiment. This just seeing how the gray color of the image is varying regarding a initial point. And then we are also trying to get some turbidity polytograph in the entrance of the gullet, but with the same technique. The results looks good at these preliminary results, but now we want to compare with experimental data of turbidity in this entrance. And finally, just to mention how we are trying to transfer our knowledge and our work to a real application. Here in this rotation tank that is managed by the University of Aalborg, we install a Raspberry Pi and a peak camera, and we are starting to measure some velocities and also depths in this deposit. And finally, a question of what is next here in this process line. So this is three cool words that we are starting with, and is the edge computing. We want to use these raspberries to process the videos before to send the final velocities as a way to try to decrease the work that is needed for all this analysis of the PIV. Then self-calibration. If we want to do this, we need to adapt the parameters depending on the condition, and also this rectification of the image that is needed, that be a little more robust. If you touch a little the camera, that everything not fail. And lastly, the data fusion. Try to different techniques, for example, PTV, PIV, some neural networks, and see which one is better, or for example, triggering the velocity measurement depending on the variability of depths on this tank. So this is all. Thank you to all, and I'm going to stop the presentation.
Many thanks, Juan. Very interesting presentation indeed. There is actually a question, and is regarding. I will relay it, and well, just let me say also out loud. If please put any questions in the user interface of GoToWebinar, and I will address to Juan. And in the meantime, there is a question regarding. Have you seen any difference between tracers, and what type of tracers do you use?
Yes, definitely. The tracer is key in all of this because we are measuring the velocity of the tracer, not of the water. So this has to be clear. And we have found that, for example, to get some let's say, depth average velocities, this is calibrated with a model. For the bubbles, we have to use a coefficient of 0.6, and for this fluorescent particle, that is filament, 3D filament extruded and cutted one by one by us, that is a coefficient of 0.8. So this is not very accurate. Yeah, so that is big numbers, but is something that we have to further study. I think that is a key point that we should investigate more. What is that influence between the tracer velocity and the water velocity, and then not only that, as what is the difference between the surface velocity and then the depth average velocity?
Yeah. Very nice. I have another question, and well, for the people that are asking, I will not refer to their name specifically because we are recording the webinar, and we have to comply with the GDPR regulation. So I will just forward the question to the presenter, but I will not mention who is asking it. I have another question, Juan, for you, and we have a little bit of time for it. Good morning, Juan. How can the LSPIV technique be applied on large surfaces? For instance, is it possible to capture the whole surface of your setup with only one camera?
Yeah, that this is like a balance between the resolution that you need for catching the particles and the camera that you have. No, for us, the maximum area that we are recording is more or less 4 meters by 2 meters. That is almost 8 square meters. So you have to use like a network of cameras or a lot of cameras to do that. And is there when this edge computing and this self-calibration can help us to not produce a lot of data and a lot of work to analyze this PIV.
Oh, okay. Thanks a lot, Juan. It was a very interesting application of large-scale PIV indeed. I think we can move to the next presenter.
Thank you very much.
So next will be Dr. Hessel Winsemius, and maybe he can share his screen. And in the meantime, well, I will introduce Hessel a bit. He's a colleague of me. He works at Deltares, but he also has his own firm where he develops very low cost and open source solutions for monitoring processes, rainbow sensing. And he will be here today presenting some work that he has been working the past years on open source solutions for image-based velocimetry in rivers. So please, Hessel, the floor is yours.
Yeah, can somebody help me how to share? Oh, okay. I can now get a pop-up that I can show my screen. Sorry, I did not realize that that is how it works. Okay, so now hopefully you can see my screen. Can somebody confirm that? Antonio, maybe?
Yes, we can see your screen. Yes, yeah. We can see your screen.
Yes, yeah. Okay, now it's okay. Yeah, so thanks, Antonio, for the introduction. For some reason, it's switching all the time. Okay, yeah, all right. So I'm speaking now a little bit about from the perspective of a project. It's called the TEMBO project, so Transformative Environmental Monitoring to Boost Observations in Africa. So it's another European project, and this is the logo, and it's an elephant. Tembo actually means elephant in Swahili. And it's also a little bit like a Lego block kind of thing, because we're trying to figure out how to put technologies together into services that work in Africa, so under African conditions, not just environmental conditions, but also the sort of the socio-economic conditions. So basically, what just to give you a little bit of perspective on the program that I'm at the moment developing, or that it's actually I would say an ecosystem of bits and pieces of software. What we're trying to achieve is that in an operational manner, you can go from a video to something like this. You've seen that also from the previous presenter, where you get information on the surface velocities and interpret over a cross section also what the river flow is. And it's really image-based measuring of discharge that we try to achieve and operationalize. Now, the software that I'm working on is called Open River Cam, and there are a number of principles that we're trying to follow, and we're also trying to really co-design it with end users. And the main principle is to, that's really on the top, to facilitate observations of Q, discharge, everywhere in any context and with any hardware setup. And the idea really is not only to bring these methods, these scientific methods into practice, but also to make sure that they can be applied in the context. So with the staff that you have available, the materials you have available, the knowledge that you have available. So it should be as easy and simple and adapted to the hardware that you have available locally as possible. And then the idea is to really move parts, and I think that is the only way that we can make technologies more affordable, to move a large part of the work actually to the value chain to the local ecosystem, so to local people, and so let them perform as much as possible of the value chain as wherever we can. Now, a prerequisite for that is that the software that we use for that is free and open source, and that it is also easy to deploy and work with. So a lot of the work eventually should move to, my work should move to more capacity building, figuring out what local business models could be, education, and we're thinking about setting up a hydromet academy together with the Trans-African Hydrometeorological Observatory, and build these local ecosystems so that this software can be used. And so basically any modification, any development that we do is really aimed at facilitating and making it simpler and making it easier to work with locally. Now, why do we choose cameras as sensors? I think it's important to reflect a little bit on that, because they're affordable and flexible. So you can they're basically also omnipresent. You can get off-the-shelf cameras in many places. You have your smartphone, but also because for this specific application, you want to have high flow events. So many of the potential users we have, they're not even interested per se in always having a camera on site, but they want to, for instance, update their relationship between water levels and flows quite regularly. And so, well, you can also do that by deploying a camera, measure a couple of events. You get lots of events, lots of observations during one event, so you can measure a whole hydrograph. And that also already gives you a good impression, if you have a site that is reasonably uniform, at least, of the relationship between water levels and flows. So, but also important, especially also in African conditions, we try to work in Africa here in this project also, is that the physical contact is between personnel, materials, and the water. You have to also reduce that as much as possible. And so I've seen rivers, like in semi-arid areas, rivers can be very low, but then suddenly they can also become very high and fast flowing. So it's actually quite hard, if not dangerous, to measure in those conditions. Now, also the methods, the image-based methods are also recognized. So I thought it would be nice to also complement a bit the work of Salvador Peña, the next speaker of Photrack AG. He did a lot of investigations in how to make it work under different conditions with different setups, hardware, and also building out a service from it. So it's really recognized as a method that can work in many conditions. Now, what does the product, if you like, look like? It's really meant to measure river flow with a simple local camera solution and do that operationally. So it's not just so we also already saw OpenPIV. We actually use OpenPIV under the bonnet of the software also at the moment. We're moving towards a more faster method at the moment. But anyway, it's the idea is that you operationalize that. So it becomes much easier to do your camera configuration, the perspective interpretation, and also in particular, if you want to do it operationally, that videos are processed more automatically. And it's really up to you to, in the morning you wake up, you go to your dashboard, you check out what was the latest video, what does it give in terms of discharge, water level, and you don't have to do anything in the process yourself. So yeah, your camera is set up locally, and the platform, the web platform, actually does the work for you. So just an example of what we can do with the software. So we had a setup in Limburg for a while. We actually had a setup together also with Photrack and Zeba, where we sort of had two setups together, but I'm not reflecting too much on that in this case. And here you can see, so each dot here basically represents, we have different colors representing different properties of the videos. So that's not so important here. So just look at the left one, for instance. You can see that each green dot basically is a video analysis with. If you look carefully, you also see a gray bar here. So there's an error bar. So the variance of the velocities from frame to frame is also used to put error bars on this. Yeah, so you can actually, within a couple of months' time, you have a very, very dense rating curve. And just to make sure that you get this, the black dots actually represent the measurements done by the water board in Limburg. And they do a measurement on monthly basis, but it took them about, I think, 2 years to collect these black dots. So they do a measurement like every month or so, and sometimes they're opportunistic and they take a measurement during high flows. They really go into the field because they know it's going to be high. But about once every month, and we have an observation once every 15 minutes. We have the ability to filter out the best observations because we have so many, and the rating curve becomes much denser. And you can start to figure out also, for instance, that does this rating curve change from winter to summer, for instance, because there's going to be growth in the banks. That is an interesting question we are now trying to figure out. Another case study. So here you can see we did, in a tidal estuary, we did experiments with a drone where we looked at, basically looked at results from different perspectives. So we looked from the bridge, but also from above, and we also have images from the side, videos from the side, and checked out how does it, with different seating conditions, how does it work? Can we also interpret these error bars? Do they make sense? So here you see, for instance, a video with a large error bar, which is good that it has a large error bar because it's actually quite off from the one-on-one line. But also, so does it here you can, for instance, see a reasonably poor estimate because there's just a very large unmeasured part. So transparent observations are observations that have very little optical solutions. So that means that you have to interpret a lot of the cross-section by extrapolation. And so this was a comparison with ADCP. I forgot to mention that. So ADCP on the x-axis and PIV, which is the method underlying OpenRiverCam, on the vertical axis. So what we currently have on the roadmap is we have a library with a command line interface. And what's important is this service layer. So on top of the service layer, you can basically start to develop a lot of stuff. So you could develop a standalone graphical user interface if you want. It's quite well documented how this service layer works, but yeah, what we currently have in the works, and it's going to be released in May, is Node OpenRiverCam, which allows you to do this automated processing. And so either by having Node OpenRiverCam in the cloud, just waiting for jobs to be supplied by the web platform, or on the edge, where it really entirely independently operates. The only thing it does is from time to time check if there's a new task on the web platform that it has to adapt its way of working. For instance, if you have done a reconfiguration or you have changed the perspective of the camera a little bit, you have to make a new task. The task will be picked up by the device and it will start processing that task with any video coming in. So that really works entirely independently. If things go offline, not a problem. It will just store everything locally in a database, all the callbacks, and once the device gets back online because you forgot to fill up your account or something for the 4G, for instance, then it will just send off those callbacks as soon as it's reconnected. Now, and then live OpenRiverCam is the dashboard that sort of orchestrates everything. So you can have multiple sites, you can have multiple node OpenRiverCam instances running in the cloud, and you can see your videos, you can see your results, your time series, etc. So this is then what it looks like in practice. And it's still under development, released also in May 2024, most likely. And the idea of this platform is you can visualize your results, you can set up new tasks, but also very important for use cases, you can interact with other applications. So you can actually, through the API, export data in standard, and we can also export data already in Delft Fuse format, so that you can import it, for instance, in your live operational early warning system. Delft Fuse is early warning software built by Deltares. Yeah, an example also that we're trying to sort of figure out how can we make this work in the context, in African context. So here's an example of a site that actually Salvador and myself will be visiting again next week in Zambia. And we're really trying to compare different methods and see if we can also mix them up a little bit. So in the middle, for instance, you see a solution by Seba and Photrack, the discharge keeper. It's a very nice software as a service with also a very nice hardware setup. But it's also quite big, and yeah, you have to really understand a lot about the setup. And it works with their own software. So, for instance, if you want to move part of your service to more local service providers, for instance, a service provider that is able to host OpenRiverCam for you, then that might actually make the service more affordable. And so we're trying to figure out if we can mix each other's methods on this site. And we're also really doing that on the hardware level. So this is one of the latest inventions of Photrack, the PT box, very nice small Raspberry Pi based box that has basically all the components to do the calculations, to make videos, to send them off to a live platform. It has all the ingredients, and yeah, can you then run both softwares on it? So we're actually establishing that now, and next week is probably likely to be sort of the first test of that. So I think that is where I want to stop. Thanks a lot. This is a nice video we took with a drone in Ghana, just to look at with an interesting visualization. Thanks a lot.
Excellent, Hessel. Thank you very much. Very nice presentation and yeah, efforts in general. I have a question for you, Hessel. Have you you deploy local cameras in rivers and they are in an open area? Have you suffered any vandalism or any issues regarding damage to the cameras due to weather or action of people, etc.?
Well, actually, no. So in Limburg, well, at the moment, not yet. So in the Limburg, we it's actually quite in the open, but we never faced any vandalism issues. We did do some fencing, so the setup is behind a fence, but it's still it's next to a footpath. So yeah, I'm not sure. Maybe we were a little bit lucky, but it is sort of recognized as an area that is sort of managed by the water board. And in Zambia, the site that I just showed, we were also a little bit lucky that we were able to put it on a place that is also not accessible by anybody except for staff of the Lunsemfo hydropower company that we work with. So there we don't have that problem. But if you put it somewhere out in the open, yeah, for sure that's going to be an issue. It's not easy to work with. But I also think that in those cases you could try to do it in a different way. Yeah? You could say, okay, let's do a temporary setup with the camera to get a rating curve, and then we have a more light and less conspicuous setup with water levels only, and we update that rating curve from time to time with a shorter survey period with the camera, where we have a little bit more control over the site and we guard it, for instance, for a while, something like that. Huh? Or you work with a smartphone solution if the stream is not large enough, where you transmit videos taken with a smartphone. That could also be an option. But then you have to have somebody close enough and somebody willing enough to really go out there in the rain with an umbrella and take videos all the time. So that is also, of course, it's not straightforward. You have to really consider those kinds of cases carefully before you make a setup for sure.
Yeah, nice. Well, we have to move on, but there is an extra question that you might address very fast, Hessel. Especially, someone is asking, especially very interested in the drone velocimetry. The question is, how do you deal with the relative motion of the drone with respect to the field of view? And how do you deal with those uncertainties, especially in low velocities? Could you address that question very fast, Hessel?
Yeah, so drone movements, I can be very quick about that. So we have a stabilization approach that uses recognized corner points to stabilize. It's also split up in quadrants so that you have stable points in every quadrant of your video. And then the second small question, sorry, what was the second question again?
Yeah, how are the uncertainties of these drone velocimetries in low flows?
Low flows, yes. Yeah, so low flows, well, it's especially low seeding conditions that you have to be worried about. So especially the library PyOpenRiverCam has a lot of methods to pre-process the frames so that you do not get spurious velocities. I think of course you can't estimate velocities if you don't have tracers, but if noise becomes higher than the signal, you have to make sure that you get rid of the noise before you actually process the video. So that is, I think, key, that you pre-process so that you simply do not get a velocity under those conditions. I think that is quite key. And yeah, there's guidance and methods available in the documentation. And documentation is also key for good open source software. And I have to say that I spend a lot of time on documentation. So make sure that you have a look at that and make sure that you really check, is my noise suppressed enough to warrant that I don't get spurious velocities that are not meaningful. So a velocity of 0, while there is actually a velocity, but simply you don't have a seeding density, it has a strong influence, negative influence on the quality of your results, obviously.
Okay, well, thanks a lot, Hessel, very interesting presentation. We're going to move to the next speaker. There's going to be Dr. Salvador Peña Haro from Photrack. Salvador is a PhD, a Mexican researcher, a PhD from the Polytechnical University of Valencia. Then he did a postdoctoral position at the ETH. And since then, he has been working on a different type of problems. I think, yeah, we have Salvador. He has been working at Photrack, a spin-off from the ETH. And he's going to present some of their work related to image-based flow and water quality monitoring in sewer systems. So please, Salvador, can you go in?
Yes, can you hear me? Can you see my presentation?
Yes.
Yeah, so thank you for the introduction. And as Antonio was saying, I will try to give just a brief overview of image-based flow and water quality monitoring systems. So now this is in the way. Sorry, I'm trying to go back to the previous. Yeah, so in this slide, you can see an animation of continuous systems, what we call the discharge keeper, under different type of rivers. On the upper left, actually that's a body which only has that event occur during 4 hours and was the only event in 1 year. And that went from 0 to 80 cubic meters per second in I don't know, like 20 minutes. So it's a very challenging place to monitor and to measure the flows. In the middle one is like German standard river. Also, we can see a flow, but not that big. And on the right, also you can see a flood event in a station in Spain. And the point of showing this animation is that you can see how the method works. Like we measure first the surface velocity, and from there we try to calculate the discharge, the volumetric flow, but also to show you how these methods have become robust. You know, they can measure during day, during night, if it is raining, when the water is lower, until the water is quite high. No? And that all is recorded just by a camera that you can see, or on the left upper and down image, lower image. There is just one camera and actually an infrared beamer to illuminate the scene during night. And all the systems are more or less similar. They just consist of a camera, a beamer, and they can be connected to the grid or can be connected to solar panels. And so the hardware setup can change a bit, but the methodology is the same in all of them. To get the volumetric flow, one of the input data that we need is, of course, the cross-section and the water level. So if we are monitoring the volumetric flow in a continuous fashion, we also need to know the water height continuously. So our systems can do it like optically if we have a well-defined shore, like it's a nice defined plane, because we only first with only one camera, and we are detecting the interface between the water and the shore. Or if that shore is not well defined, the system can get the water level for external sensors, for example, a bubbler or a pressure sensor or radar. We can connect those devices. The other ingredient is the surface velocity, of course, and to get those velocity vectors also that we saw on the two presentations before, the image have to be treated before. There can be some image enhancement, then they are auto-rectified, and depending on the type of processing, PTV, PIV, STIV, or many other type of PIVs, there are different treatments to the image, but the end result is that velocity field. And then how to treat that velocity field and how to go from there to the volumetric flow. So in our particular case, we also use a surface velocity envelope, that blue line on the right image, which is a curve fitted to the velocity measurements. We obtain those velocity measures analyzing a 5-second long videos. I'm going to come back to that velocity envelope. But then we have to get the volumetric discharge, we have to convert those surface velocities to depth average velocities. For that, there are also like different models. So there are very simple models that they just use an alpha value, that they multiply that the surface velocity by a factor. Will use the 0.85, but there can be also some other empirical models or more physical-based models. Or also I'm going to say something in the next slide. But before, I just want to show some pictures of other systems, these continuous systems. And I was saying they just mainly camera, infrared beamer, computing power at the edge, and can be with solar panels or can be connected to the grid. And one of the big advantages of these image-based methods that they are not in contact with water. So as we were seeing on the first animations, even on the floods, probably you didn't see it, but on the right animation, after the flood, when the water is coming down, you can see that the concrete structure was heavily damaged. And the camera being far away, it's always safe. So it's and also besides being safe, in a safer position, is needs less maintenance. So now I want to come back to that velocity envelope to showcase also another of the strengths of these methods. In the animation at the left, we see an ensemble of different, many measurements done at the same water height. And when the animation moves, it represents the velocity and the surface velocity at a different height. So that's a probability distribution function of the most probable value of those velocities according to a certain water height. So then we start getting a more probabilistic value, not just at one measurement. And also that can be used to detect changes on the river. For example, changes on the cross section. That is represented on the image on the plot on the right. So on the y-axis we have the velocities, and the x-axis represent the water and the river width. And those lines, each line is for a given time at the same water level. And that line should be the same. But as we can see, it is dynamic. And that means that the river most likely is getting sedimentation and the cross-section is changing. So that's one of the strengths and beauty of having so much data and seeing the whole river width. Same technologies can be applied in different environments. For example, can be used to measure in urban environments. This is a flood event that we process those videos which were downloaded in social media and then were post-processed. And those videos, we were able to calibrate those videos to get those velocities in meters per second by using, for example, the dimensions of the house or of the door. And while probably the results are a bit more uncertain, they are very good and they are very helpful to evaluate the flood hazard. And now moving a bit from rivers, like they are a bit big, which can measure a 100-meter wide river, to another dimension. These three examples on small canals, which the left one is a overflow or combined sewer. The middle one is 16 centimeters wide canal that is the entrance to a wastewater treatment plant. And the right one is a manhole and the sewer of around also 40 centimeters wide. And on the right one, actually the camera was mounted on top of the manhole. And here we see a comparison of that one with an ultrasonic sensor that was mounted at the bottom of that canal. And again, the camera was mounted a couple of meters above the water. Sensors that are in contact with wastewater require a lot of maintenance, which the camera does not. Just a small comment that this same technology has evolved. No? It's also, we can have it available in a smartphone. Now we can, and all the processing is done inside of the smartphone. But coming back to the urban environments and to the calculation of the depth average velocity, when we see that the ratio between the canal height and width, so when it's getting narrower, we can see that there are the secondary currents of the flow, they produce sub-deep velocities. So the maximum velocity is not at the top of the flow. So which then to convert from surface velocity to depth average velocity is a bit more complicated. So actually now also inside of CoUDlabs, we did extensive experiments to really try to measure that velocity depth and improve that conversion from surface velocity to average velocity to get a more accurate volumetric flow under these conditions. Also, between these CoUDlabs experiments, we run an experiment in a longer time frame where sedimentation occurred. And the same as I was showing on the example before on that river, that we could see that footprint of the surface velocity changes. Here we can see it also very clear that the blue line is at the beginning when there is no sediments, and the red line is with the sediments. And actually, by analyzing this difference, we can even get an estimation, like an idea of how big is the sediment at the bottom. So now I would like to move to the second part of this presentation, that is water quality. So we also can measure some water quality parameters. So in this case, I'm showing an example of turbidity. So I'm going back now to rivers. And in this case, we use machine learning, a CNN model, to train the model to detect turbidity and also color dissolved organic matter. So actually, the graph that you see on the bottom right is a comparison. Well, yeah, so it's a measure CDOM and the one that we measure with the camera. And that camera is only RGB. So the idea also is now to see if we can measure other type of parameters by using other type of cameras and other type of illumination. So we are starting some tests to see if we can use a camera that is sensitive on the UV to the visual spectrum, and we are using an active multispectral illumination. And so this is also very much in the feasibility stage. And we did, in a laboratory, we did some tests to see if we could measure turbidity and the COD. And by this, we just took a very small cup with artificially made samples with different values of turbidity and COD. And we illuminated with with 13 LEDs, which they have a spectra at different wavelengths. And then with the camera, we measure the intensity that is reflected, brought back to the camera. So here is an example of the reflectance spectra of different samples of water, different combinations of COD and turbidity for the 13 different LEDs. And also underneath, we can see the value that was measured by the camera, predicted, compared to the reference value. And this we knew perfectly well, the reference value, because we're synthetic samples. And we got a very, very good match, which is very encouraging. And now we are trying to go back to the site here and try to get more that is shown on the right, to try to get other parameters and see if this technology can be used to obtain other parameters, for example, ammonia. And with that, I thank you for your attention.
Thank you very much, Salvador. Really, really impressive collection of many different applications of optical observations, indeed. I have a question regarding the bathymetric changes in the river. Have you had the chance to validate that at any reach? Because it's a very, very interesting application to see how the morphology of the riverbed changes over time, and that influences your optical observations of flow.
So we have very few data. We have actually on the example that I showed, we then got some ADCP data and we compared, we saw some changes, but it's only qualitative. We don't have anything quantitative. And this is what we tried to do on the sewer example that we did at Benz on the CoUDlabs, because then we know exactly how much sediment was accumulated and we have the whole series. So we are trying to see if we can infer how much sediment is there.
Oh, very, very nice, and it would be very nice to see that moving forward, and well, along with the other very impressive applications of continuous monitoring of velocities across many different environmental conditions, which is also quite impressive. Thanks a lot, Salvador.
Thank you.
We will move to the next presenter, if Giulio can join. The next presentation will be provided by Dr. Giulio Dolcetti from the University of Trento. And Giulio is a postdoctoral researcher working on hydrodynamic monitoring on environmental and hydraulic sciences at the University of Trento, but he did quite a lot of work before at the University of Sheffield on a number of techniques regarding acoustic observation of surface roughness in open channel flows. And I hope that today we will talk a little bit about that context and some of his further work. Thanks, Giulio, for being here, and the floor is yours.
Thank you, Antonio. Thank you. Do you confirm you can see my screen now? And do you hear me?
Yes.
Okay, that's great. Yes, so the work which I'm going to talk about today was done while I was in Sheffield. I was working with Simon Tait, we were presenting later on, and also was done in collaboration with Newcastle University and Matthew Burks, who some of you probably know. He did some work on some nice work on PTV especially. And here I will be talking about how to use water surface waves in order to estimate the discharge in rivers and open channels. And I really enjoyed the presentations today. I get very excited whenever I take part in this kind of events. I'm a fan of image-based monitoring techniques, and I'm very happy to see how quickly it's progressing as well throughout the years. There are in these methods, I think there's a lot of potential that they can be extremely powerful. There are also some limitations which somehow we need to address. And some of them were mentioned already by Juan, by Hessel, and by Salvador as well. The first one is that, as the name says, it's called particle imaging or particle tracing. So we need to see traces. We need to see trackers on the surface that move along with the flow in order to estimate the velocity. And while it's true, and both Hessel and Salvador, they showed nice applications where we didn't actually have artificial traces, but we're using just surface waves or ripples instead of the traces. We have to bear in mind that sometimes those ripples, those surface patterns, they don't move at the speed of the flow, but they have their own dynamics. And we try to quantify how big the error is if we don't take this into account, and it can be, there is a bias, which can be as large as 100% depending on the flow conditions. The other limitation or challenge, if you like, is that most of the times we don't really want to know the velocity, but rather we want to know the discharge and the flow rate. But for this, we need to know depth average to surface velocity index, which we can guess, we can estimate quite accurately now. But also we need to know the bathymetry and depth. And now in Trento, I work on mountain rivers, which are steep, which have a very mobile bed, which are not easily accessible. There is no bridge, most of the times, no way to measure an actual cross-section. So most of the uncertainty, at least in my experience, sometimes comes from not knowing the bathymetry or even just an average water depth. So we wanted to see if we can do something about it. And we started by realizing that the water surface responds to changes in flow conditions. We can see it with these two images taken on the same river at different times. And clearly the scales and also the behavior of the water surface, the shape in general changes a lot with the flow conditions. So we asked ourselves whether we can use this change in order to estimate the actual flow conditions. We've done some work on characterizing the dynamics of the water surface. So we start from that basically. And what is established is that there are different types of patterns. We have what are called turbulent buoys, scars, vortices. These are direct manifestation of turbulence. And these are actually the patterns that move along with the flow. But then we also have gravity waves, capillary waves. These are like ocean sea waves, and they move, they propagate with their own velocity in the different directions. And most of the times, even though they're not always easily recognizable, both patterns actually coexist. So to distinguish them, we use what is called the frequency wave number spectrum. So we take a Fourier transform, we identify the frequency in time of a wave, for instance, and the wave number, which is like a spatial frequency, tells how many wavelengths per meter we have. And the ratio between these two properties tells us the speed of the wave. And we can model it, especially for gravity waves, quite accurately, but also for the turbulent buoys. So this is what a typical frequency wave number spectrum look like in a flow. And we can distinguish the turbulent buoys that have a constant velocity, which is close to the velocity of the flow. But also we can see that gravity waves can be faster if they're propagating downstream or slower if they're propagating upstream. So there's like a Doppler shift induced by the flow. So essentially what we do is we start with the idealized flow which it is described in this case by a linear velocity profile, and it's defined by a few parameters, for instance, the velocity and the water depth. And based on the theory, based on these parameters, we can create these diagrams of these frequency wavelength number spectra to see how they react to changes in the flow. And we can see that as we increase the flow velocity, there is a shift, there is an increasing frequency of the waves which are going up, downstream, and a decrease for those going upstream. So it's a Doppler shift, like I mentioned earlier. But also we can see an effect of the depth. So especially the long waves, they are slowed down when the depth becomes smaller. So there is a decrease in their frequency. So if we can detect these changes in the measurements, then we have a way to estimate both the velocity and the water depth based just on the dynamics of the surface. The method is not entirely new. In fact, in oceanography, it's been used since the Second World War, when they used it to reconstruct the shape of the bathymetry near the shoreline to decide where to land on the French coast. There have been very, very few applications in rivers in conditions which somehow are more similar to the ocean, so with relatively low velocities and low turbulence, and only focus on the velocity. So we try to combine basically these two previous approaches. And I'll show briefly how it's done. So we start with a video. Basically, we start with a collection of images which have already been rectified, and we select a certain window. So we have a signal in space, in 2 dimensions in space and in time. We take a Fourier transform of this signal, so we end up with a 3D spectrum, Fourier transform in all the directions, which is the 2 components in wave number and the frequency. And this is our measured spectrum. Then we guess some values of the depth and the velocity, and based on these values, we can construct an ideal, a theoretical spectrum. And we can change those guesses and run an optimizer in order to find the values of depth and velocity, which give us a better fit between the measurement and the theory. And this tells us basically the depth and velocity that we can use to estimate the discharge. It's as simple as that, basically. So we've done a test on 2 different rivers across different flow conditions, different illumination, weather, with rain, without rain. And these are some of the results. So this is the estimated depth against the measured one for both rivers. So with a reasonable accuracy of the reconstruction for all the conditions. And these were the rating curves which we reconstructed. So here our reconstructions are the red dots, and then the black and the gray dots are the official Environment Agency measurements for those same conditions. And these are the time series basically of the depth and discharge, where we see how reconstructions, again in red, just to see that we were able to take into account even of fairly dynamic processes. Now we can see here somehow that we have higher uncertainties for the higher flow rates and higher depths, and this can be explained. It's basically because, as we can see here, the sensitivity to depth variations is much smaller than the sensitivity to flow velocity. So depth doesn't have a very strong effect on the spectra. So in order to measure this accurately, we need to focus on the waves which are more sensitive to depth. And these are fairly long waves. They have a wavelength which is about 2 pi, or 6 times the water depth. So we need, first of all, these waves to be present on the water surface, and then we need to be able to measure these waves. So we need effectively a window size, which is about 10 times the water depth for accurate depth estimation. So in our case, it was a relatively narrow channel. So we had to do use a window which was basically almost as large as the whole river width. So basically what we reconstructed was an average water depth and an average velocity. This depends on the geometry of the system which is investigated. If the bathymetry is known instead, then for the velocity, we don't have this constraint about the resolution. We can use much smaller windows. We can distribute them along a transect, and we can reconstruct all these nice distributions of the velocity and combine them with the bathymetry. So as we would do with LSPIV or PTV or STIV. So we took part into an inter-comparison study in 2020, and our method was working fairly well compared to the others as well. But with the advantage that it doesn't need tracers, and when it doesn't use tracers, it takes explicitly into account the dynamics of the waves. So we expect this to be more robust when there are no tracers and when there are visible gravity waves, especially. We've created open access MATLAB script, which you can download. If you want to use this QR code, you will find it there. And it's the very first version, so if you want to help us, give us any kind of feedback, would be highly appreciated. Also, if you need help running it or want to discuss anything, just get in touch. We'll be very happily assist you. And just to mention, we've done some application using acoustics as well instead of videos, and that's to overcome the other challenge, which is the one of the illumination as well. So thank you. Here again is the QR code if you want to test it, and thanks.
Thanks a lot, Giulio. Very cool presentation. Another one in the list. Very good quality applications. I have a question for you. I guess you decompose the frequencies, the spatial and temporal domains of different wavelengths. But I would like to know what is the extent of the effect, for instance, of changing orientation of the sun, that will directly influence the way that your camera see the geometry of the wave itself. So the effect of sun glint, and perhaps other processes like rainfall that will create other other signatures that you don't have normally in those clean images.
Okay, yes, good questions. I start with the last one. That's okay. So everything which creates the waves is good for us. So it doesn't matter if it's the wind or turbulence or the interaction with the bed or rain. So any sort of ripple, in the end, the waves will respond in a similar way, as long as they're not too big and that they become non-linear. So in that sense, rain could actually be an asset. It could actually be useful. And as for the orientation, there is basically the mechanism that allows us to see the waves is the fact that we see the reflection of the sky gradient, so that the color of the sky changes with the azimuth angle. And then when the waves change the orientation of each reflection point, then we see a different point with a different color, and that gives us a link between the slope of the surface and the light intensity. So there is an effect of the orientation of the camera. I tried, for instance, it doesn't work so well with drones because they're looking from above, so they're not too sensitive to water waves. And there is somewhere in my experience, I'm not sure if it's possible to maybe do some calculation and find an optimal angle. But in my experience, it works best at not a grazing angle, but sort of. So in that sense, that is optimal in terms of the visibility of the waves. But then we have to take into account the distortion introduced by the rectification. So it's sort of a I don't know, finding something in between, yeah. if that's okay.
Yeah, excellent, Giulio. Very nice, and it's a completely different method, which and as you mentioned, it's quite also popular in the oceanographic and coastal waves and satellite-derived bathymetry, depending on wave refraction and diffraction in different places. And it's yeah, it's a quite nice technique that ported to rivers is opening a new way of estimating bathymetry and flow at the same time. Super nice presentation, Giulio.
Thanks, thank you.
Well, thanks a lot. We are at 10:40 at the moment. Let's do a small break of maybe 5 minutes. We can take a cup of coffee or tea, and then we come back in 5 minutes at the, or yeah, let's do 4 minutes for a very fast coffee cup, and then we are back at 11:15. So see you in a bit. Well, then I hope you had a not so long coffee break, but we are back with the program. In the first part of the morning, we had several very interesting presentations. Most of them relate to computing flows, estimating velocimetries in rivers, and so on. And in the second part, we will have a few more, also in a slightly different but very complementary topic, and it's on the use of also optical observations, but to monitor different processes, especially using deep learning. And we will have 3 presentations on different concepts regarding deep learning applications. And then at the end, we will have an extra presentation on the use of optical monitoring for water quality processes, direct monitoring of water quality variables. So now in this presentation, I'm going to give, or I would like to give a kind of an overview of what is deep learning, and present at the same time some applications that we are working on in different processes related to hydro water quality and quantity processes. So if I can change my slide. Yeah, so just to introduce, we are talking about the world of computer vision. And in computer vision, what we want is to generate automated routines to extract information from images or videos coming from cameras, from satellites, from acoustic sensors, from anything that will generate a sort of image-like observation. We want to deploy algorithms that automate the extraction of actionable information on them. Typically, what you had up to 5 to 10 years ago, it was classical computer vision that will rely on the description of filters or heuristic methods. That is, imagine that you are looking for detecting a bright orange ball in a grassy field. You will have to specify the type of colors that you're looking for, the type of geometry that you would like to extract, and then you will create a tailor-made filter for that. We can also apply other mathematical techniques to extract features of interest, like edges or other processes. However, these methods are normally very sensitive to the environmental conditions. So in the moment that we have slightly off thing that we did not prepare our filter for, their performance degrades very fast. And then, therefore, this computer vision was classically oriented to laboratory conditions in which we can specify very well and in a very repeatable way the environmental conditions, or to industrial applications where you have a very repeatable process, but they had very little applications in the field. But then that has changed since the last 10 years or so, thanks to the advent of deep learning. And in the context of imagery, what we work or what we talk often with deep learning is the use of convolutional neural networks. Just to explain briefly what it is a neural network, as you know, is a mathematical formulation in which we try to replicate the behavior of brains or the connectivity between neurons. And in the context of convolutional neural networks, it's a type of neural network in which we create convolutional filters. That is a filter that you iterate or you mosaic along the image, and then you create a feature space. If you compose many of these convolutional filters in a sequential or a parallel manner, and you create many layers, that's what we call a deep convolutional neural network. And in such a way, what we create is an architecture in which we supply an image or a video or a tensor or a collection of frames from a video. This image is processed sequentially with these convolutional operators, and then is downscale, upscale, until we have an output of our desired form. And in practice, that's what has been taking form in the practical application of these convolutional neural networks for image processing. We have had for a while already what we will call a narrow artificial intelligence for vision. So those are different models that are more or less generalistic, and they can already address many different vision tasks. And what you have typically is what we call an encoder classifier scheme. So you will start with an encoder in which we try to provide an image, downscale it, and apart from these operations, we try to extract some classification task or some lower dimensional representation of this original image. And those models are trained with orders of millions or billions of images that we can extract from internet, for instance. So you have collections and repositories of images that you have an RGB image and a description of the image, a label or a bounding box. So using these labeled, pre-labeled image repositories, we can train these general encoders. Then when we go to the practice, like for instance, an hydro-environmental engineer, we use what is called often transfer learning. Is we take part of this network, we augment it with some, like this would be an encoder, we augment it with another transfer to our output objective, like this will be a classification task, this will be a segmentation task. So we want to see the different types of surfaces that are in an image. And then by supplying a much more limited number of images, we will train this model for our particular use case. And that is called transfer learning because we're using the weights or the parameters that were already trained with billions of images, and we're just tweaking them a little bit for our particular case. That allows us to use general vision learned processes and tailor them in a realistic way to different types of applications in our field. So just to give you an example, for the last few years, we have been working on different methods to monitor fat in pumping stations. Why is that important? Because in many urban drainage systems, you have the accumulations of solids and floating elements mixed with fat, oil, and grease that hardens and creates surfaces that threaten the performance of pumping systems. And till now, there was no way of monitoring these processes except having someone opening a gate every month and checking what it is and telling you how filled of fat, oil, and grease your pumping station is. But we had a couple of projects in which a number of colleagues from Deltares, from the Water Port of Limburg, the municipality of Rotterdam, and Arnhem were involved, where we created a network of cameras that we could deploy at different locations in pumping stations. So we created a network of 8 pumping stations with 11 cameras, in which they were observing the processes inside these pumping stations during a very high frequency during a year and a half of observations. And we use this kind of pre-trained neural networks. We adapt them to our particular case, in this case, differentiating between the extent of pollution in a pumping station, and then we retrain them for our particular case. We managed to get a quite good generalized algorithm across our 8 pumping stations, in which we could monitor effortlessly the dynamics or the very high frequency and very low frequency dynamics of these fog or fat, oil, and grease processes. And that allows us to create comparisons or to create analysis with the operations of pumps or the hydrodynamics of the local pumping station, etc. These kind of segmentation models also allow us to create other derived variables. Like for instance, by monitoring the extent of the pool water, we can create optical gauges to monitor the water depth. And we can also use that information to correct in real time for changes in the elevation of the water surface in order to do particle tracking velocimetry or image velocimetry and assess flows. These applications do not only work in a pumping station where you have pretty stable environmental conditions, you don't have that many changes in lighting conditions because you set them and so on, But for instance, in the field, we can already deploy robust segmentation routines with these convolutional neural networks. So here you have an example of some work that we have been doing on tracking the presence of floating vegetation in different reservoirs and creating early warning schemes for intake systems in power stations. So with these kind of models, we can already generate robust solutions that can be deployed in the field. And in the field, you have changes in lighting, changes in weather, you have weighting in your surface, you have all sorts of things passing in front of your camera. But with a good training data set, you can generalize those processes already with these deep learning approaches. And we have been talking a lot about camera base or CCTV camera base or something quite close, but we can apply these routines in many different types of platforms. So for instance, we have a lot of work on the monitoring of reservoir dynamics. And in particular, in the last 5-10 years, a lot of countries, they have developed their hydraulic infrastructure very fast. And sometimes the public records of this infrastructure lag a little bit behind. So we have been working on different solutions in cooperation with the World Bank and the Japanese Risk Assessment Agency in order to generate solutions that can monitor the Earth surface continuously and detect whether there are new reservoirs being built. And then that will allow us to inform better national inventories of areas where governments do not have complete control of what's being built and where. And we have been working on this detection of reservoirs, but also on extracting relevant features from dams or other hydraulic structures that have relevance for risk analysis. For instance, we have been working a lot with the extraction of dam bodies from remote sensing data, in which this time we don't have an RGB image as before, but we have a multi-spectral image, and also we have a multi-variable image, in which you have, let's say, optical features, you have infrared, you have digital elevation models, you might have radar observations, and we need to train this sort of encoder-decoder segmentation models in order to identify the extent and location of dams in this case. And how does the future look like? So in the short term, we see that we get more and more general vision models for optical observations, RGB especially, because the data sets are very large already. But we see these techniques being ported to other types of images, like thermal plumes in space and time images, or radar or sonar, etc. And we will keep having more generalized models that can work with those input spaces. We also have approaches that are working already with multimodality, so mixing imagery, segmentation of imagery, and text, and zero-shot models, so generalized models that can generalize vision tasks and work even beyond training sets. So in the next few years, it's expected that we will see more of those applications like the segment anything model from Meta right now, in which we will have real general vision task models. And with that, my presentation is over, and I don't have anyone to moderate myself. But if anybody has any question, I will gladly address it. If not, we can go to the next presenter. That this will be Simon Tait. So Simon is a professor, quite veteran professor from the University of Sheffield, and he has a lot of work also on optical methods for hydraulics across many different domains, but especially related to urban drainage. And today, Simon will present some work on applications of deep learning for asset monitoring in urban drainage systems, and especially underground infrastructure. So
Thanks, Antonio. Can you see my screen now?
I can see, but it's not the presenter screen.
Okay, how about this? Is that the
Yes.
presenter screen? Yeah. Okay.
Yes. So the floor is yours, Simon.
Great. Thanks, Antonio. I just want to talk a bit about a piece of work. It follows on quite closely in the information that Antonio's given you, and it's looking at an issue in terms of the management and operation of sewer networks. This work was done by one of my colleagues and myself, Esran Kazemi, and it was part of the CoUDlabs project. Just to give you some historical context, there's about 3 million kilometres of sewers in the EU, and basically the technology it's been used to collect information on their condition has just been taking CCTV cameras through these pipes, and then generally the images are manually examined, although that is now changing. If you look at the pictures, you can see that the top two pictures on the left are sort of show you a sort of sediment deposit or a sewer pipe that's structurally degraded. This has problems because when these sewers collapse or get blocked, you obviously get flooding on the surface, or you get overflows, which should only operate during heavy rainfall, actually operating most of the time. So traditionally what's happened is that images have been examined manually. That is slightly changing now, and they match against defects that were developed in the 80s. And on the right hand side you can see a sort of defect coding system. It's very complex. They get longer and longer, and at the moment in the EU there's around about 300 defect codes. Japan, there's 10, and when people have looked at the use of these complex defect coding, basically you'll find that the error level is 20–30%. So there's a lot of defect misreporting by the manual examination of images. So that's the historical context. There are efforts now to automate sewer defect identification. As Antonio said, a lot of the earlier efforts or current efforts use classical computer vision techniques, such as threshold and feature extraction. Now, as Antonio explained, these were developed for high quality environments. And when the features are extracted and people use sort of classifiers such as random forest classifiers, they have significant issues. People try and use larger and larger data sets, but the success rate doesn't increase very much. So when people are using these sort of feature extraction type methods, you're typically getting maybe 80% identification for joints, which are a very clear feature that's well defined. But when you look at a feature that has much more variable sorts of image features, such as holes, then you're down to a success rate of 20%. There are companies that are continuing to use this approach using much larger image data sets, but the success rate is not increasing significantly. I'd like to talk about a bit of work that we've done in Sheffield where we've simplified the classification defect system and, as Antonio said, used a more deep learning approach, which should require a much smaller calibration set and is much more suited to a variable image environment. So in terms of simplifying the defect coding, we've gone down from 300 to 5 classes with 13 subclasses, and we've based that on the prevalence of defects and the defects that have significant impact on structural integrity. So we're looking at blockages, intrusions, joints, cracks, and instances of severe damage. So what we've done with the deep learning approach, as Antonio explained, you need smaller amounts of training data. So we've created a training data set of about 1,500 to 2,000 images. We've taken the simpler defect structure and we've created this labeled data set. We use an open source deep learning framework called YOLO 9, YOLO version 8, and I'll show you a few examples of using this small training data set to see what sort of success we get with these significant defects. So in terms of the images that we've used to train the model, you can see that I've given you a sort of frequency plot of the images or defects within the data set that we've used. One of the issues using deep learning approaches, Antonio says, is you've got to define a bounding box that contains the artifact that you wish to look at. So on the right hand side here, you can see some manually applied bounding boxes in the training data set that highlights defects such as joints or deposits or cracks or structural defects such as holes. What I've shown you here is you can see the labeled data sets on the left hand side, and then we've used that as part of a validation data set, and it's provided you with some confidence, and confidence in deep learning looks at both the precision that you make your prediction and also looks at recall, which is the ability not to make wrong decisions. So the numbers here indicate the confidence that we would have in properly identifying a defect and not making an incorrect prediction. So if we take the trained model, and it was trained, as I say, with about 1,500 images, and then apply it to other images, you can see that in the vast majority of cases, the confidence is much higher than 0.5, and for particular defect types such as joints, blockages, the precision is much higher than about 80% for the vast majority of defects. Still slightly struggles with defects such as perforations and holes, but it is significantly better than the feature extraction type codes, and it uses significantly smaller image data sets to train it. So all the code is available. It's open source. If you look at the DOI at the bottom there, so we've got code that assists you labeling. It trains the algorithms, the conventional that are in YOLO software, and we've also given you some defect examples as well. So we would welcome you trying to use it and to see if you can get a similar level of performance that we found. So thank you very much for your attention, and hopefully it's an indication of a sensible use of image analysis to deal with a practical problem that's found in sewer and drainage networks.
Thanks a lot, Simon. I will have a question regarding this. I guess like a very, very critical part of having good models for classification of defects is also having good training sets. How is the landscape of open source or shareable or even standards across the industry on having these defect labels? You have mentioned this difference between the European Union and Japan, but is there any prospect for having a standard?
The standard for the defect classifications across different countries, certainly in the European Union and Europe, are very similar because they just had a similar historical root. The reason that the Japanese standard is so different is that the Japanese haven't collaborated with other countries. So the defect classification standards in the US, places like Australia and Europe are all very similar. So they're all very complex. They all have a very similar coding structure. The Japanese had a much simpler coding structure because they never followed the same historical pathway. But the complexity of the defect classification structure doesn't give the people that operate these systems additional information. You get the same level of information and make the same level of decisions whether you use the Japanese classification system or the more European ones.
Yeah. But in terms of generalizing models, I guess that's relevant because the data sets will have to be, well, maybe you can have a Japanese and European model together.
You could, but you can compare the results from two types of analysis and look at the identification of really critical defects, and both systems come up with almost similar defects if you use it on the same set of CCTV data.
Well, thanks a lot, Simon. There is no more questions for now, so we'll go to the next presentation. The next presenter is Professor Joao Leitao from EAWAG ETH. Thanks. So Joao will be here. Joao is a professor at ETH and EAWAG. Joao has a quite good portfolio of many different applications of optical sensing. But today we're very excited to hear about the extraction of these opportunistic sources of data from floods and in urban systems. Joao, the floor is yours.
Thank you, Antonio. Just a quick question. Which screen are you seeing?
We are looking at the wrong screen.
Okay. All right. Now it should look better, right?
Yes.
Okay, good. So, Antonio, thanks a lot for the kind words in the introduction. Yes, I've been working on several topics that really look into new opportunities to use images that are collected by citizens, that are collected by municipalities to really increase the availability of flood data. And today specifically, I would like to present you the study developed by a former PhD student, Priyanka, on estimating floodwater depth from social media images. This has been a collaboration with colleagues from ETH Zurich. And just a little bit of background. As you know, the flood events have been increasing over the last decades, and this has to do mainly with climate changes, so more extreme events, and these extreme events more frequent, and also to the increase of urbanization. So we turn our space, our cities, more impervious, and then we end up with larger amounts of runoff and less infiltration, for example. And this causes problems to the managers of the urban water systems or urban drainage systems, problems of those taking into account the future planning, and also those involved in the rescue when these natural hazards do happen. We can then use models to improve our drainage systems, to simulate and assess flood risk, and then support risk management. So there are different ways that we can then use urban flood models or urban drainage models, but what is in general applicable to all models is that models do need data. Of course, they do need data, input data, but also we do need data for model calibration, so just the model parameters, so that the model output is similar to the observed flooding in this case. And for model validation, get an idea on how certain simulation results are comparing to past events. We can also use then data and models together to really inform flood real-time alert systems. So for example, we can have a real-time model, and then if we have observations here and there, we can update the model so in a data simulation fashion. The problem is that the traditional methods to estimate flood data, they rely in many cases on remote sensing, satellites, satellite imagery, which are not looking into all corners of the Earth all the time. And this makes extremely difficult when we think about urban pluvial floods, which are relatively short events. We have to be lucky if we have a satellite really focusing on the area where these events take place, that will usually last half an hour up to 2 hours. Another possibility is that we have these rules spread all over the city, and then we can get an idea of the maximum water depth. But we then lose the dynamics of these flood events. So then it's clear that some new measuring techniques are required, and then this comes to this possibility of relying on social media, because 90 million new photos and videos are posted on Instagram only every day. And it's not difficult to just make a quick search on the web to find lots of people happy taking photos in the middle of the water in floods and so on. So the question that we try to answer was: is there any value from social media images to estimate flood water depth? And these are these 3 images, for example, are images from a flood event that happened in Lisbon, in Portugal, in December 2022. And as we can see, although it was happened during the night, we still get some photos during the night taken by people. As Antonio just mentioned, our approach is based on machine learning. It's a multitask deep learning approach. I will not go into the details here. We tried different ways of models, a regression model only, a regression model with multiple data sets, and the latest development was a regression model coupled with a ranking model. And basically, one is we have the ranking is basically the regression. We look into labeled images and put or assign a water level into each of these images and then train the model. When we have the ranking, it's a pairwise ranking loss. We just basically provide to this trained model 2 pairs of images, one with less water in the image, one with more water, and then we tell the model which one has more water to help predicting the flood depth at the end. So as well as Antonio presented what is behind these computer vision and machine learning models, we started with about 25,000 images, which I have to say it's not really a huge amount of images, where we could classify different objects, persons, cars, bicycles, buses, buildings, and so on. And then we collected around 8,000 flood images, or images with a flood in the flood of flood events, and again annotated each one of these images for the flood level, and also identified the object classes in these images. Here we have these 8,000 images. We divided this in 2 data sets to use once for the ranking and the other one for the regression. And what is behind all these things? So then we assume that that the different objects have standardized sizes or dimensions. And we used human beings, bicycles, cars, buses, and buildings, and divided them into different levels, from level 0 to level 10. And for each one of these levels, we have assigned a range of water depth and assigned the median or the mean value for each one of the levels. So basically what we are looking at is what we see in the photo is what are the parts of these objects that are outside the water, and then since we give them each object a standardized dimension, we can estimate what is underwater and then estimate the water depth. So this happened a little bit before the segment anything from Meta being available. So we had to annotate these images in a manual fashion. And here in this image, we can see a person that we had to somehow identify the building behind, and then we segment the part that is water, and then also here painted in pink. As I said, we run 4 experiments. The first one we call regression, trained with regression loss on the DF object dataset. Regression plus, we train with the 2 datasets. We have the classification approach, and then we have, as I mentioned, the combination between regression and ranking. And moving on to the results, we could easily, from these images, detect the objects. As we see here in this example, we have 2 persons, 4, 5 cars, and water, and then the model easily classified and identified the objects in the image. And then on top of that, we could assess or predict the water level. This is not a trivial task, because in this image, although we do have a water depth here, we see the full body of the persons there, and the cars are in the water, and then we have different levels here. And how do we do that? And we ended up using a trimmed mean, which basically excludes some of the predictions, some of the objects, to then be able to calculate the average water depth in the image. Of course, this adds here some uncertainty, but there's no way to, or we could also have a distribution, would also be possible. We would like to have kind of a specific information about this water depth prediction. This is another example. So 2 persons, they give, although they may have slightly different height, they will provide the same water level. And this is another example that we see 2 cars and a person inside the car. Of course, we could predict the water level in the 2 cars. One is a little bit in a more deep water depth than the other. So level 4 in the car in the foreground, level 3 in the car in the background. And then this person, of course, it's outside the water. We see the full body is level 0. And again, this causes these difficulties in assigning what is really the water depth from these images. Just trying to summarize a little bit the results we got. So basically, the average root mean square area is between 10-15 centimeters. And what we could see was that by providing this combination between regression and ranking, the results improve a little bit. When we talk about the level, not the centimeters of the water, but where the level, then we can also see a small improve. And of course, what we can also see here, when the regression plus and we use all the 2 data sets into the training, we ended up with a better predictions than when we just have a relatively small amount of images. And I have to highlight here that the amount of images that we've used is relatively small for what is commonly suggested for this type of applications of computer vision and machine learning. And this can be again seen in these these box plots that we assess the results for each one of the levels. And then what we can see is that the quality of the prediction decreases when we do have higher levels or higher water depths. And this has to related to when we have images on level 9 and level 10 and so on, we end up having less images from these because people get water up to the head. So then it becomes very, very dangerous, and then we have the amount of images we had to train the model becomes much lower. This is just 3 examples. In general, this regression and ranking approach works good, although when we have images that are very complicated, like this one that we see on the right-hand side, that we see a car almost submerged, this would be easy for the prediction, but what we also see in the image is that the water stands still and then reflects the buildings, and this increases a huge difficulty in this computer vision method. So then, as we can see, all the methods that we tried are really far from the ground truth from the image. And then coming back to the real event, that I know more or less where these things are, these places are, and what really happened. We see these photos, and then we can see what can we get out of these things, out of the method, the prediction method that we've developed. So basically, we do have an indication of the object that is identified in the image with a probability, and here in this case we see that the object class in the green is a car with a probability of 0.99, and the water depth is class or level is 5 with a probability of 0.6. The same thing is valid for the person that we can see in the image. The same similar results in the image in the middle and the other one. So then without these things, nobody knows exactly how was the water depth in these images. But if we can rely on images, this alternative data source, we can bring information into flood management and flood modeling. So basically, to finish, I think I can say that we are able to estimate flood depths automatically directly from images. Of course, there are many possible improvements that we can think of. So, for example, is combining text and images for increased performance. So we can think about, usually people text when they post these images, they text something along with the images, and we can also try to make use of this information, as well as other studies looking into using this text in the social media to really understand the severity of floods. One of the problems that when we use these images is that most of them don't have location data, although most of the phones, most of the cameras nowadays add the coordinates, X and Y coordinates, into the metadata of the photos, but then social media platforms, for security reasons or just remove this thing. So then this is a problem, but perhaps a way to go and to explore is if we know that our cities have many surveillance cameras spread all over the areas. So if we could get access to these cameras and then estimate in place, we don't need to send the images here and there, but estimate the water depth in local and then send them to the decision makers and flood rescuers, then this could be a way to go. So if you like to know a little bit more details about what I just presented, so this is the paper that we have published a couple of years ago. Thank you for your attention.
Thanks a lot, Joao. Again, very nice presentation. Another one, and it's a super nice source of opportunistic data sets indeed. But I have a question for you. What do you think it will be the future of this coming in? You have mentioned that georeferencing is a problem. but will there be an option on using already preset observations from Google Street Maps or previous imagery to try to georeference these spatial views? Or what do you think in terms also on the technology of phones, what they can bring to complement these observations?
Yes, for me, the easiest way to go is to rely on public surveillance cameras, because we know where they are installed. They are spread in many of the cities, so it will be relatively easy to get access to these images or videos or frames of the videos. This would be, for me, the easiest way to go. Another way to go would be to create, and this is not new, to create a platform where people could upload images specifically for flood depth information. And with these, we will make sure that we know people will ask the people contributing to add these extra metadata, for example. I don't know if this answers your question, Antonio.
Yes, kind of, because I guess then if you have, let's say, a fixed CCTV camera in a place, you have observations before and after the flooding. So you also have a lot of cues regarding lamp post or signaling or other features. You already have like a exposed view, right?
These would make the estimation easier, because we could easily identify objects in the image, or in the scene that is seen by the camera, and then easily quantify. We don't need to estimate or to standardize the height of the population or the size of the cars or something like this. We could directly measure things from the objects in the scene.
Would you see as an option in the future a classifier for the type of cars that can give you the actual height of the cars? It's a quite standardized. It's the same vehicle. If you have the model and so on, you could get a real observation of height, right?
Yeah, this will be nice to know exactly which car model we are looking at into the photo, and then we can easily estimate the water depth. It would increase the accuracy of the model. I just want to mention something that might be relevant. We are assuming that all the objects are touching the ground. If that's not the case, that can happen. All these estimations of the water depth might be a little bit erroneous.
Yeah.
Just to mention this thing, because this is important. This is also an assumption that we have to make, and it is wrong.
Eventually, perhaps you could, if you have the model of the vehicle, for instance, you could know what is the displaced internal volume, and you could estimate what will be the height in which you might have this bias, right?
Yes, these would be ideal ways to go, and definitely interesting. These would require a huge amount of data, and to train these models. The problem is always to train the models. I believe that if you do have more data, we can increase the quality of the prediction of the water depth, or the estimation of the water depth. And something that I think it will be nice to discuss in our communities is how should we share this data? My data set, I'm happily sharing this thing with everyone. But if you could combine all data sets together so that everyone could increase the training data, for example, this would be a huge step ahead or forward.
Well, Joao, thanks. Excited to see how this evolves in the future.
Thank you.
And we will go to the next speaker and last. That will be Pierre Lechevallier. Pierre is a postdoc, is a doctoral researcher at EAWAG, the same group as Joao. And unfortunately, he is not present here today because he's in Australia, and the timing is not the most appropriate, but he kindly recorded his presentation. And I think the Deltares studio will share a recording of Pierre. And should any question arise, one of his supervisors, Joao Rickerman, a group leader from EAWAG, is also here afterwards to address questions regarding this research. Can we share the video of Pierre?
Hello and welcome to a brief presentation about the measurement of wastewater quality with camera. My name is Pierre and I am a PhD student at EAWAG, the Swiss Institute for Water Research. Today I want to share with you the reason why we believe that spectral cameras have the potential to become a future tool for the measurement of water quality. I also want to introduce you the concept of multispectral and hyperspectral imaging, and finally I will share some results I obtained with the hyperspectral camera for the measurement of turbidity, organic carbons, and other pollutants. On this slide you can see a really simplified overview of my PhD. I designed experiments to capture images of wastewaters, and afterwards I train models that will take as an input those images and try to give as an output a prediction of water quality. The models I am using are either based on linear regressions or more sophisticated neural networks. I don't have time today to develop too much about their details, but I will give you at the end of the presentation a link if you are curious to know more about the specificity of those models. So the first step is always about capturing images of wastewater, and in the next slide I'm going to explain to you the concept of hyperspectral imaging. So you can see on the right side of the screen how a conventional camera that everyone has in his cell phone works. The camera is actually sensitive to three colors, the red, the green and the blue, and the sensor is going to combine these three channels to make a colored image. When we move from RGB cameras to multispectral and hyperspectral cameras, the only difference is that instead of capturing only three colors, we are going to capture more colors. The extreme case of imaging is actually the hyperspectral imagers, where the sensors are sensitive to hundreds of colors. For my experiments at EAWAG, I am using a hyperspectral sensor which is sensitive to the visible and near infrared range. In other words, the camera I am using is able to acquire spectral reflectance in the range of 400 to 1000 nanometer with a 2 nanometer resolution. In order to develop a model that will take as an input a wastewater image and give as an output a water prediction, a water quality prediction, I collected two different datasets of images and reference pollution measurements. The first series of experiments happened in a laboratory setup. You can actually see a picture on the left of your screen. I placed in a small black cup some wastewater samples, and I acquired with the hyperspectral camera, as I mentioned before, for each one of the 144 samples I generated, I acquired hyperspectral acquisition. For this setup I used the halogen lights because these types of lights is emitting wavelength also in the infrared range. For each of the sample that I took a picture from, I also made some laboratory analysis for reference pollutants such as organic carbons, ammonium, turbidity, and so on. You can check those data actually, they are available online at this link. After making these quite successful laboratory experiments, I transitioned toward the flume. In this open channel that you can see on the right, we circulated some wastewater from the nearby sewer at EAWAG, and we installed along the flume different sensors that were monitoring continuously the wastewater quality. So in this flume we had, for instance, a turbidimeter, S-scan absorbance probe, and hyperspectral imaging taking pictures of the wastewater surface. This experiment lasted 6 months, and I'm going to use both the results of the laboratory experiment and of the flume experiment to show you the efficiency of cameras for the measurement of pollution. Let's start with turbidity. On your screen you can see on the left side the measurement of turbidity from the lab experiment, and on the right side the measurement from the flume experiment. In the x-axis of the graphs you always see the reference turbidity values, which means that they are the values measured with conventional sensors. And on the right side, on the y-axis of the graph, you actually see the predicted turbidity obtained with the models I trained with the pictures. So basically, you can see on this graph comparison between the prediction of the camera models and the reference measurements. And the closer the points are to the red line, the more accurate the sensor is. So in the case of measurement of turbidity, we actually have a very robust models that for both the laboratory experiments and the flume experiments are able to give a turbidity estimation quite close to the reference measurements. So from this first analysis, we can already conclude that camera, or at least hyperspectral cameras, are able to measure turbidity and also suspended particles from the pictures. Let's move on to ammonium. The measurement of ammonium is not as good as turbidity, but it still looks quite promising. From the laboratory datasets, we are able to have a really good estimation of ammonium. When we move to the flume experiment, we see that the ability of the model to predict ammonium is a bit worse compared to the laboratory experiment. But the model is still able to understand the trend of ammonium and to give, let's say, a middle good prediction. We are working on the improvement of such models, and there are two things that we are exploring now in order to improve the estimation of ammonium. The first is to try to have better models in themselves, so to tune the parameters or to calibrate them in a better way. And the second thing we are trying is to capture different images, and more specifically images that are also containing information about the ultraviolet range, because we know that ultraviolet range might be quite relevant for the measurement of substances such as ammonium. Finally, let's have a look at some results with organic pollution. Sadly, I do not have yet the results from the flume experiment, but in the lab experiment, similarly to ammonium, we see that the model based on the images from the hyperspectral camera is able to estimate dissolved organic carbon relatively well. So, to conclude today's presentation, I think, or I hope that I convinced you that images or cameras are quite interesting because they make it possible to measure fast and also remotely some wastewater contaminants. The method is looking quite promising, especially for suspended solids and turbidity, but also it might also work for other pollutants, and we are still working on it. As of today, we are constantly trying to improve our models, and we also explore other imaging technologies, specifically the ones that are sensitive to ultraviolet light. Okay, thank you all for your attention. It was my pleasure to share with you some of my research. If you want to have more details about this research field, you can check out either my website or the website of Jörg Rickermann, my PhD supervisor. Feel free to send me an email. And of course, if you want to have more understanding of the specific methods we are using here, you can check out our latest paper. Let me finish by acknowledging all of my collaborators. Thank you all for your attention and have a great day.
Thanks a lot, Pierre. You will hear this in the recorded video, but maybe if we have any question, Jörg can connect. Hello, Jörg.
Hi, Antonio.
It's a very nice research, the one that Pierre is doing, and it's a pity that he cannot be here today to address any question. But maybe you can, Jörg. And I would like to ask, like, to which extent do you believe that the spectral characteristics of these particles will be representative across different catchments? And also, what would you expect to be the influence of small lighting condition changes in sewers, or have you addressed that in any way at the moment?
Yes, that's very good questions, Antonio. I think the particle characteristics will be difficult. But as we know that absorbance spectra, like the submerged spectrometer probes, like spectralizers and others, they are okay, right? And turbidity probes are also okay, whether they work with a 90-degree angle or not. I think this is probably better than nothing, right? And if we talk to practitioners, one big argument against monitoring water quality is that it's so complicated, right? And especially the maintenance and the calibration of the sensors repeatedly, and the toilet paper, that's like a big step. On the side note, I think these images might also be improving particle monitoring, especially of grab samples or filters, because I would expect that sand particles would give you a very different reflectance than clay or some softer particles, right? So you could possibly also get size distributions from filters with these things, right? Not online, but very fast lab measurements, right? And the second point was, help me again, how transferable this is from one catchment to the other? Oh, yes, I have no idea. And the lighting conditions. Yes, at the moment we are making our path as we go, right? So we would like to have a model which would predict spectral response, also taking into account the environment we're working in, whether your water is 5 meters away or half a meter. That clearly makes a difference. And we are not there yet. In the project where we collaborate with Photrack, we also try to look at different lighting estimations, and we actively illuminate the scene, right? So that might actually help.
Mm-hmm. Yeah, and in a sewer you can sometimes control the lighting conditions, so that probably helps. Yeah, it'll be good to keep a look at what Pierre will be publishing in the next years, or in the next months, because yeah, it's a quite fundamental question that he's paving the way in some instances. So I guess it will be a bit far away still from practice application, but having a non-contact optical sensing for water quality is the holy grail, right, Jörg? To have a less maintenance application.
Well, I don't know whether it's the non-contact thing, but something which works and which is affordable, that would be very, very nice, right? And if we start with turbidity, we know that particles have a detrimental effect on the environment.
Yeah, totally. Yes. I have one last question myself. I don't see anyone ask, but I have installed cameras in sewer systems. It's a non-contact but contacted application, because the lens deterioration is quite a thing, especially where you have gases and other type of debris being accumulated in the lens. Are you at the moment actively trying to have that as an extra variable, or that will come at a later stage?
I think that comes at a later stage. In the collaboration with Photrack, we target at the moment the inflow of wastewater treatment plants. And we've been working, or some experience we have is with housing the camera, right? So making it behind some glass screen or so, which might alleviate the problem a bit. But Yes, I think we will never reach the precisions that lab methods have, right? Like the precautions these people takes to like keep the temperature of the light source, right? To check the stability, all these things. This is like, I think this is not like realistic, but it's probably also not needed to have an idea which water is polluted and which is rather unpolluted.
Yeah.
And of course, the physical basis for this is non-existent, right? This is all correlation based, like the submerged spectral, like spectrometer probes that we're seeing. Yes, for the organic stuff, there's like some chemistry behind it, but the rest is all correlation based because people use the toilets in the morning, right, and no wastewater in the night.
Yeah, true. Well, let's see. We will stay tuned for what comes from Pierre research, and thanks a lot, Jörg, for addressing the questions.
Thanks, Antonio.
This was the last presentations of the day, but I would like to invite also Jörg, don't escape. I will like to invite all the panelists back, if they can share their screen. I think unfortunately Hessel had to leave before, but we have here a quite good sample of the presentations today. Yeah, before closing the webinar, it has been a pleasure to have you here today and to have these different views. Does anybody want to comment something on the view on the upcoming applications of optical monitoring and so on?
Maybe I can say something. I really enjoyed all the applications of neural networks and machine learning, and I think there's a lot of potential and most likely a future in there for any kind of monitoring, whatever variable, whether that's velocity, water quality, and everything. But I think that to achieve that and to achieve that more quickly, we need to start thinking about building like common shared repositories maybe for data, because we will need a lot of data to take into account all the different variables and applications. So I think I'm happy that there are such initiatives like CoUDS, which help bringing together different labs, and perhaps we need to bring this a step forward in that direction.
Yes, I really liked when you, Giulio, you showed that you had a repository with a QR code where you share your code, you share your data. Like for instance, the work that Salvador is doing in CoUDlabs, and every experiment that we do in CoUDlabs is then being published as hopefully as a journal article if it's a novel thing, but we guarantee that the data is also published in repositories like Zenodo, where other people can access and can check. Can reuse the data for other applications even, or for further research. And I think that really will pave our way towards collaborating and performing joint research in many fields.
Yeah, Antonio, I'd sort of support that. I think it's important to share code and data because other people can get value from it, and that adds value to the originator.
I think also, as I mentioned this thing, I think this is really an important point, and it would be nice if you could share our data and then also share code, basically share the knowledge.
Yeah, I don't know how you view it, but I also, when I started working with optical measurements, it started as a hobby, kind of, and it all started thanks to OpenCV, let's say. So libraries where you can access scripts, publicly available, server with good documentation, and you can start doing your first steps into the field. But it's fundamental to have shareable code, shareable repositories, and build upon the work of many people. I think that's fundamental for this field and many others, but I will see that the computer vision field has a very it has had a very good component of this sharing libraries and data sets and so on so far.
Yeah, but something like, well, for instance, even water companies can actually participate if they have cameras or if there are any source of data. Just can dump it somewhere, maybe with some common requirements for the data.
Well, then we're approaching 12, so I think it's time to close. It was a real pleasure to have you here. I think it's a good, healthy outlook at what techniques are being applied and what is upcoming in rivers and sewer system monitoring with optical sensing. And yeah, I will be very excited to keep looking at what you produce and what other colleagues produce. But today we had a good sample of across different disciplines also. So thanks a lot to all. And well, we will close the webinar here. Thank you very much for attending, and goodbye.
Thank you for organizing.
Thank you. Thanks for organizing.